Don't worry.
Actually need it.
Keep it short.
How's your semester going? It's really greater than or equal to 2 jobs, isn't it?
I think, at least I think I'm enjoying it.
So you asked after Yuri. There
Yeah, I know. I saw him. I was asking if you were still coming in or not, so it's good to see you. Good. It's like turbulence then. Like turbulence then. Intermittent. Yeah.
Okay, welcome. We're very fortunate today to have as our speaker Jim Stone, who's a professor at the Institute for Advanced Study in Princeton, and formerly a professor at Princeton, and actually formerly chair of the department. Jim got his PhD at the University of Illinois in 1990, and before going to Princeton, held faculty positions at the University of Cambridge and University of Maryland. He has received many, many accolades. He's a member of the National Academy of Sciences and the American Academy of Arts and Sciences. He's won a couple of prestigious medals, and he's an inaugural fellow of the American Astronomical Society. Jim is a pioneer in developing very flexible and versatile computer simulation packages for studying astrophysical processes that involve magnetohydrodynamics, radiation physics, and general relativity. He has used these to produce groundbreaking results. He and his collaborators and students have used these to produce groundbreaking results on systems that range from protostars and exoplanet formation to black hole accretion and the intracluster and intergalactic medium. I met Jim, I remember distinctly when I met Jim, it was at an accretion disk conference in Paris in 1990, and I remember 3 things about that conference. One was meeting Jim.
Wow.
One was the fact that during the conference, Hubble announced that its optics didn't work and they would have to fix it. And the third was that a group of American participants in the conference, involving neither of us, tried to cash traveler's checks at a blood bank in Paris. They sort of saw Banque du Sang and Anyway, today, Jim is going to tell us about astrophysical fluid dynamics at exascale. Jim Stone.
Thank you, Mitch. Thank you for a very generous introduction. And now I'm wondering what I did at that meeting for you to remember it so long ago. So it's a pleasure to be here, and a pleasure to be a visiting fellow, which means I'll be here for a couple more weeks. So I'm happy to chat to people while I'm here. Because I wasn't sure the audience of this talk, I sort of prepared a more general presentation, thus the very general title, Astrophysical Fluid Dynamics at Exascale. And so I think I need to start by giving a bit of a motivation about why astrophysical fluid dynamics is such an interesting topic and some of the methods that we're using to tackle these problems. But the reality is it's such a broad and diverse subject, I have to focus on something. And so I'm going to focus on applications on black hole accretion flows, because that's something we've been working on a lot recently. So much of my talk will really be about applications of these methods to black hole accretion flows. Say something at the end about challenges. Feel free to interrupt me if I'm going too fast, or if you have questions. I'm more than happy to answer questions as we go. Otherwise, let's just dive in with a motivation. And that's easy, because pretty much everything we look at in the universe is a fluid or a plasma. Starting with the planets, so a highly processed image from Juno showing all this structure in Jupiter's atmosphere. The sun, of which there's enormous expertise here on studying solar corona and convection, all through fluid dynamics at MHD. And now galaxies as well, of course, with combined HST, optical, and JWST infrared images. You see not only the stars, but you see the infrared emission from the gas and dust in the galaxy. You see how complex these systems are. And so basically, all of the big questions, understanding how planets, stars, galaxies form and evolve and what their structure is, involves understanding astrophysical fluid dynamics. And so it touches just to so many issues. So how would we tackle this problem? How are we going to study fluids? Well, if these are really fundamentally plasmas, and so the most fundamental description you can imagine is solving the Vlasov equation plus Maxwell's equations for the electric and magnetic fields. That really is only necessary, though, for collisionless plasmas. Fortunately, if the mean free path for collisions is small compared to the system size, and it doesn't have to be Coulomb collisions, it could even just be collisions with waves or fluctuations in the media, anything that isotropizes the distribution function, then you can treat the plasma more like a fluid and take moments of it and get the standard or hopefully familiar equations of MHD, magnetohydrodynamics. So continuity equation just expressing conservation of mass, momentum equation, an energy equation with the appropriate Poynting fluxes for the magnetic field fluxes, and an induction equation to evolve the magnetic field, just one of Maxwell's equations. And the system is closed by an equation of state, which comes from the fact that the distribution function is Maxwellian. You can make that closure. And so this is a very, very powerful system of equations, much more simplified than having to solve the full collisionless system. And even, in fact, in some cases, for weakly collisional plasmas, you can still use this MHD equations, but supplement them with extra terms to represent the anisotropic viscous stresses and heat conduction you get in weakly collisional plasmas. So you can add so-called kinetic MHD terms, which I think is still a frontier in trying to extend these equations towards understanding weakly collisional plasmas. So we're all on the same page. This is the mathematical model. These are the equations that we're going to be solving with numerical methods in the lecture. So in general, those equations don't have analytic solutions. Of course, there are some in special cases, but generally, you're going to need numerical methods to solve these equations. And by now, this is a very rich topic. There's courses on computational fluid dynamics. I can only just give you an overview, a very brief overview, sort of classifying methods by approach. You can either discretize the equations on a mesh, a spatial grid, and that leads to methods like finite difference methods or finite volume methods, central schemes. Or you could discretize them in spectral space using so-called Fourier methods, or more popular are so-called discontinuous Galerkin methods, where you discretize using piecewise polynomials on a spectral mesh. Or you could use particle methods, Lagrangian particle methods. SPH in astrophysics is the best example. Each of these methods has their strengths and weaknesses. For what I'm going to discuss today, we're only going to talk about finite volume methods. They've emerged as very robust and stable methods for treating highly supersonic compressible flow. And they're also extremely accurate. They're competitive, I think, against spectral methods. And so that makes them very, very interesting. They also work extremely well on the high-performance computing systems. And so this makes them extremely useful for modern research problems. So where are we with high-performance computing systems? Well, today, as you can tell from the title, we're at exascale, meaning 10 to the 18 floating point operations per second. And even astrophysicists, 10 to the 18 is a big number. These are big computers that are very, very capable. There are now 2 systems in the US available for open science. I'm sure there's many more systems used by the AI companies, but these are the ones open for open science. One is at Oak Ridge called Frontier. Another is at Argonne called Aurora. Each has a peak performance of around 1.5 exaflops. That's roughly 1 billion times faster than the Cray XMP that I began using when I was a graduate student. So an increase in 1 billion in performance in one career is quite remarkable. Imagine if your telescopes were 1 billion times more capable than when you started your career. That's just staggering to me still. But there is there's still issues with these machines. One is that each vendor has their own programming model. They don't just run C++ or Fortran out of the box. You have to use their programming model. The most popular programming model, for example, for NVIDIA is called CUDA. Many people have CUDA codes, but neither of these 2 machines have NVIDIA GPUs in them. So you can't run CUDA codes on these machines. You have to use something else, either HIP or SYCL, which is what they support on those machines. And so what do you do when you have to write a different code for every different machine? That's just untenable as a research scientist. But fortunately, computational scientists and computer scientists are very capable. They've developed libraries that get around this problem, and the library that we've come to rely on is called Cocos. It's an open source code project. It's just a bunch of C++ templates and abstractions that you compile with your code. It's just plain vanilla C++. It essentially acts like a translator. It takes your C++ code and it translates it into CUDA, or it translates it into HIP or SYCL or whatever programming model you choose at build time. And so that gives you performance portability. You can write a single C++ code and it'll run on any architecture, even on your iPhone if you want. It supports iOS. So you can run it on essentially anything by writing a single code. And that's now enabling sluggo computational scientists like myself to be able to run on any kind of machine we want. There are many others adopting this approach, and there are other kinds of approaches, but I'm a big fan of this one, and it's nice to see these things emerging. Okay, so with that said, we've recently rewritten the MHD code that I've been using for doing astrophysical applications for quite a while into Cocos, calling it now Athena K. There's a new version of Athena K. It's a rewrite because GPUs and heterogeneous architectures have new degrees of freedom that you have to program for. You have to worry about where you put the data, where you're going to do the computations, which memory space, which execution space. And so it does really require a rewrite of the code. But once you do it, it allows you to take advantage of the performance of these machines to add more modules. So for example, not only does it have the AMR framework of Athena, but now it also includes hydro and MHD solvers for GR, SR, non-relativistic flows, but also a dynamical space-time solver for solving Einstein equations and doing numerical relativity. It has an MHD solver that works in dynamical space-times, so you can look at MHD in evolving metrics. It has a radiation transport module that also works in relativistic space-time, so you can do full GR MHD radiation transport. And particle solvers that allow you to follow cosmic rays or Lagrangian tracer particles. And I'll say a little bit more about some of these modules. So Cocos and C++ enables you to write code that can implement all these physics on these machines. This code is publicly available on GitHub. And the table is just to point out, there's not so much the numbers that are important, but to point out that it works on my old laptop, which is an M1. I just got a brand new one, which has the M4 on it, but it doesn't matter. It works on the Apple Silicon, which is not the x86 compatible. It's actually, an ARM processor. So it works on ARM processors. It works on Intel x86 processors. It works on NVIDIA, AMD, and now the Intel GPUs as well. And so it's able to run effectively across all these different architectures, which is really what's fun with it. OK, so let me turn to sort of applications. And before getting there, though, you have to sort of worry, OK, is this code correct? Is it giving you the right answer? The papers that describe these methods have many dozens of test problems, and I won't show you them all, but one validation problem I like is a code comparison for things like the nonlinear regime of the KH instability. This is a challenging problem that you want your algorithms to get correct. It involves a resolved shear layer. So this is the instability between two fluids which have relative motion between the two. And in certain circumstances, this interface is unstable. It has explicit viscosity and heat conduction so that there's explicit dissipation in the problem. And with a resolved interface, you can reach a converged solution to the problem. If you run a high enough resolution, you can reach a converged solution. So we've done that using the spectral code. The image, each row is a different time in the evolution of the KH instability. And each column is a different code. The rightmost column is the spectral code run at 4096 squared spectral elements. And that's the converged solution for this particular initial value problem, a single perturbation of this KH instability. And what's important is that these finite volume codes recover exactly the same solution, pixel by pixel, as the spectral code does, at somewhat higher resolution, 8,000 squared spatial grid points as opposed to 4,000 spectral elements. But because the finite volume methods run so much faster than spectral methods, it's actually cheaper to do the finite volume solution and recover spectral accuracy for this particular problem. You can even compute the L1 error versus time and show it's converging away. So we know quantitatively that our solutions are, for a complex turbulent flow, emerging from this instability are in agreement with other spectral methods. So that's kind of reassuring. And I won't show you other test problems, but hopefully I've convinced you that the methods are accurate. These finite volume methods are accurate. And another advantage of them is they give you excellent weak scaling on highly parallel systems. Because they involve domain decomposition, you just break the mesh up into chunks and give each processor a different chunk of the mesh and only communicate the boundaries. That makes them very efficient. So the performance of the code measured in zone cycles per second versus the number of GPUs it's being running on are nearly perfect straight lines in all these particular examples out to hundreds of thousands of GPUs. Well, actually, it's only 64,000 GPUs. That's what the largest machines have. And it doesn't matter whether you're doing numerical relativity with AMR, a binary black hole merger problem, or whether you're doing GRMHD in a dynamical spacetime in which you're doing both numerical relativity and fluid dynamics. You're getting similar scaling and performance. Perhaps the better number is this scaling efficiency. What is the performance per GPU compared to running the code in just one GPU when there's no communication at all? And you're getting better than 80% efficiency, about 90% efficiency on the full machine. So again, you're getting nearly the entire peak performance across all 64,000 GPUs. So it's going to give you an ability to solve very challenging problems. So let me say a little bit more about some of these new physics modules. This numerical relativity module was developed in collaboration with David Radice at Penn State and his group using these high-order finite difference methods, which map really nicely to these sort of AMR techniques that I'm using. Actually, the challenge is the initial conditions and extracting the waveforms. In relativity, that's even a more challenging problem than doing the evolution of the system, it turns out. And so, but that's been sort of all implemented over the last few years. We're now doing a bunch of interesting problems with Franz Pretorius at Princeton and just pure gravity involving binary black hole mergers and mergers of boosted black holes. And we're extracting the waveforms. You see the usual chirp signal followed off by the ring down, by the normal modes of the remnant object. And the different colors show you that the waveforms are converging at fourth order as you would expect for these methods. And so this is enabling a whole new set of problems. Because it's running on an exascale machine, you can tackle extremely large relativity problems that are difficult to do using other methods. And so there's a whole new set of problems being tackled with that. And then again, we have the fluid dynamic solvers also working in these dynamical spacetimes. And so one of David Radicchi's students now at the Institute, Jacob Fields, is working on looking at binary neutron star mergers. Again, at unprecedented resolutions at exascale, you can get down to sort of tens of meter resolution, which is getting down to the neutrino viscosity scale. So you're getting down to converged solutions for these neutron star mergers. The movie is showing you such a merger resulting in a highly spinning remnant object, which after it sheds a little bit more angular momentum from these spiral shocks and waves, boop, it forms a little black hole in the middle. And again, you can measure the emergent gravitational waveform. This is obviously an exciting field in multi-messenger astrophysics, is to be predicting the gravitational waveform, as well as looking at the electromagnetic signatures you're going to get from these merger problems in the future. If only LIGO would see a few more neutron star mergers, it would be much more exciting yet again. We've only really had that one. And then in addition, we have these particle modules that allow us to integrate motions of cosmic rays or Lagrangian tracer particles, which you can use to trace the flow. Let me just demonstrate the particle module by an application that Drummond Fielding and Philip Kempsky and a few others are calculating, which is to look at propagation of cosmic rays in MHD turbulence. At exascale, you can now do 10,000 cubed simulations of turbulent boxes quite regularly. There's now several papers which have reached these resolutions by James Beattie and now by Drummond Fielding. The movie shows you the emergence of structure in the current density in an MHD turbulence simulation. This is a periodic box in which you drive turbulence through a forcing function and then look at the spectral and spatial properties of the turbulence late in the evolution. You can see how the turbulence cascades down to small scales, and you see the emergence of tremendous small scale structure shown by these blowing up little volumes. You can see this current density in these small volumes is highly structured, highly intermittent, and very, very strong current peaks forming in the turbulence. What's important about exascale is that quite literally, calculations that took years, so the calculation that James Beattie was running took almost a year to get through a CPU cluster through the queues. You can now get it done in a few days on an exascale machine. Again, as long as it queues. It's not the computer time that's limiting, it's the queuing system. How long you sit in the queue waiting to run is the limiting factor of getting these jobs through. So these become regular now. Now you can do parameter surveys. They're not just one-off hero simulations. You can actually study the effects of changing the magnetic field geometry and strength on the turbulence. And what Philip Kempsky at Princeton has been doing is running charged particles through the complex three-dimensional magnetic field structures that emerge. And so here's a blow up of a little tiny region in this 10,000 cubes box where he's followed the motion of a few individual particles, colored the path by the magnetic moment mu, which should be conserved if in ideal search, if the magnetic field wasn't changing its strength, if the field was completely uniform, it would be conserved. But you can see it's not conserved. You can see the particle is scattering off of magnetic field inhomogeneities, which are on the scale of the Larmor radius. It's not only changing mu, but it's also allowing the particle to diffuse across magnetic field lines. And so he's been able to test this against a quantitative theory for charged particle diffusion and turbulence. And it's been really quite interesting to see the results enabled by capturing this range of scales. Now, one last additional physics module that I think is important for the rest of what I'm going to say is radiation transport. And radiation transport is in many ways more challenging than the MHD sector of the flow. That's because it's like solving the Vlasov equation. It's basically the Boltzmann equation for photons. And so it's a multidimensional system where you need to incorporate the effect of photons in many circumstances where the radiation energy density is large. So for example, accretion onto black holes, at high accretion rates, the energy density in the photon field is much, much higher than that in the thermal pressure of the plasma. And so you need to, in order to get the dynamics right, you need to incorporate the effects of the photons. But solving the radiation transfer equation is challenging for First of all, there is an algorithmic issue. So first of all, it's taken us a long time to develop this module because the first step was writing down the covariant transfer equation in a form that could be solved conveniently using known numerical methods. And that form is this flux divergence form. It turns out you can write the transfer equation in a strictly conservative form where the time rate of change of the specific intensity plus the divergence of a bunch of fluxes, spatial flux, angular fluxes, a frequency flux, because in GR there's redshifting and so the frequency's changing, but they're all perfect divergences, equals the right-hand side, sources and sinks. So since this is a hyperbolic conservation law now, you can use all the machinery that's been developed for solving the fluid equations to solve this equation. And then it's only a matter of discretization. We have to not only discretize in space, but also in angle. So in every grid cell, we have to build a new angular mesh. We use these geodesic meshes because they give you nice coverage of the 4 pi steradians. And each spatial cell has to contain many, many, many angular points to be able to resolve the radiation field over the full 4 pi steradians. So it becomes a large phase space to resolve both all the angles and the spaces. But again, this is where these powerful computers excel. It's highly parallelizable, and so you can do the full GR radiation transport on these machines. And so I'll turn to now trying to apply these methods to looking at black hole accretion flows and the high luminosity limit. And again, I think here in Colorado, I probably don't need to tell you about the magnetorotational instability, but it's a fundamental process that gives you angular momentum transport and accretion in magnetized plasmas in orbit around a central object. In Keplerian shear flow, these magnetized plasmas are unstable. And the little movie is showing you the evolution of the current density and the production of turbulence in a little small patch, a little local patch inside this accretion disk, schematic picture of accretion disk. So you're seeing the emergence of the MRI and turbulence, which then produces angular momentum transport accretion. The resolution used for this calculation was typical of what's been used to date, typically around 1,000 cubed is considered a challenging high resolution calculation today. So what we've been doing lately is try to use Exascale to push that forward. Same data, the same variable, but now this is an 8,000 cubed box. This is an 8,000 squared slice. And this is the current density now. Now you can see this tremendous small scale structure emerging. You can see these long current sheets being formed. You can see plasmoids. In fact, you got to sort of blow up a region to really see the full resolution of the calculation. You see little plasmoids forming along current sheets. Not every current sheet has resulted in reconnection. In fact, the vast majority of current sheets are not involved in reconnection because they're not actually a change in sign of the field. And so trying to understand the small scale structure of MRI turbulence at these resolutions now has become possible. And we have a project now running a series of high resolution MRI simulations in the shearing box to look directly at the properties of this MHD turbulence.
Color scheme? What does it tell you? What's the color telling you?
The color is telling you the magnitude of the current density. So the burned out red is the strongest positive, and the burned out blue is the opposite.
Negative.
Yes, right, exactly. So we don't want to just do the ideal MHD MRI turbulence. Really, what we're aiming for is these radiation-dominated cases. So we've been also able to run these kind of calculations, not at such high resolutions, but still GR MHD calculations of the evolution of the MRI. These are now global calculations where you start from a donut of plasma. It's weakly magnetized. MRI grows, generates turbulence. But in addition, you're following the photon field. You're following the emission and absorption radiation produced by the accretion flow and seeing how it changes things. And this is a calculation. This movie starts late in the evolution where an accretion disk is set up, and it's now sort of reached a steady state accretion flow. This is now a radiation-dominated accretion flow onto a black hole. And you can compare to what it looks like when you don't include the radiation field, and it's really quite different, even qualitatively. You see the turbulence is much fluffier. This is the density field, log of density, and so this is a very fluffy. You see lots of little bubbles and low density regions embedded in the torus. That's where the radiation pressure has opened up a bubble in the fluid, and the density sort of been evacuated from that region. It's a well-known property of radiation-dominated turbulence is that it's highly compressible, and you generate much larger density fluctuations than you do when you only have gas pressure. And you also see that the material is sort of collecting in a denser midplane. That's just from radiation cooling, allowing the denser midplane to emerge. And so what we've been using lately is a survey of radiation-dominated black hole accretion flows around stellar mass black holes, where we can use frequency-independent gray opacities only. So we only need one frequency bin to model these systems because they're so hot, everything is ionized, and gray opacities is accurate in this regime. And we've been studying the initial conditions involving these sort of thin tori, so-called Chakrabarty tori, with different initial magnetic field topologies. And we've been evolving the flow into super Eddington, where you're many orders of magnitude larger than the Eddington limit, near Eddington and sub-Eddington flows, also studying different black hole spins, and as I mentioned, different magnetic field topologies, to try to understand what are the basic properties of radiation-dominated accretion flows around black holes in this regime. And so just some of the highlights, so super Eddington accretion emerges quite naturally in this circumstance. It forms a very thick radiation pressure supported disk with a strong outflow. So these are slices, poloidal slices through the three-dimensional calculation. For a calculation that's 88 times Eddington, and a case that's 0.8 times Eddington, and 0.1. We don't get to choose what the mass accretion rate is. It emerges self-consistently from the MRI, but that's why there's sort of weird numbers, but that's why we are able to sort of reach different regimes by changing the amount of the mass density of the initial conditions. And so we get super Eddington all the way down to sub Eddington. The near Eddington flows have this gas pressure thin disk with an optically thick corona, quite thick above that. Whereas the sub-Eddington case, it's all the way down to a gas pressure supported thin disk plus an optically thin corona on top of that. And so you might think of these as being certain states of X-ray binaries, and maybe these are ULXs, and we're trying to compare the properties of these flows. And you can look in a little more detail from this super Eddington case. These are the radial profiles of various quantities in the flow, spherically averaged now. So we're looking at the spherically averaged radial profiles. And it's sort of interesting because they look so different. In the super Eddington case, it's all radiation pressure. The red line is radiation pressure. It dominates by orders of magnitude. And when you get down to these time scales, the thermal time is much longer than the inflow time in the inner regions, meaning that the photons are trapped. There's a so-called trapping radius, and that photons within that trapping radius, about 20 Rg, are all flowing in. The inflow time is shorter than the thermal time. Notice the thermal time is different than the radiation diffusion time, and that's because these are highly turbulent flows, and most of the energy transport is not by radiation diffusion, but by turbulent transport of photons. And that's what sets the cooling rate of these flows and where the trapping radius is. And on the other hand, these near Eddington flows, they're quite different. The radiation pressure is much smaller, roughly comparable to the magnetic pressure in the midplane. You see radiation viscosity. The red line actually emerges as being quasi-important. Maxwell's stress still dominates, but actually you see radiation viscosity is peaking up in the inner regions, something that actually, if you don't solve the full transport equation, you don't get the radiation viscosity correct. And then again, the thermal time in these sub-Eddington flows is much less the inflow time. There is no trapping radius. Now the disk can cool, and so a larger fraction of the energy generated by accretion is going to escape in this case. And so again, we're able to probe the structure of these disks, compare them to previous predictions of what that should look like for various regimes. One very important characteristic of these flows is that they're produce powerful jets and winds, as you might expect, especially the super Eddington case. So the right columns here are showing the large-scale structure out to a few thousand Rg of the flow. And the color is not density, it's the optical depth per gravitational radius. And so for the flow to be optically thin for 1,000 Rg, this needs to be 10 to the minus 3. And you can see that that's nowhere in the volume. This wind is very optically thick. It's this dense equatorial wind which is being blown off by both radiation pressure and magnetic forces. And so a very strong characteristic of these super Eddington flows is this strong equatorial wind. Very narrow column where you can actually see down to the accretion flow along the axis. You get a relativistic jet being produced in the very inner layers, and a bound region where the disk itself, where the Bernoulli number is less than 0, so that's bound material extends. It's a very, very, very puffed up, thick region. What's interesting is these efficiencies. So this is the ratio of the energy released in radiation compared to m dot c squared, how much is being released by accretion. And you can see that only 0.5%, in percentages I should have said, only 0.5% of the energy is actually escaping to infinity. That's because it's so optically thick. There's this trapping radius. Everything's just basically going in the hole. And that goes up to more like 4% in this near Eddington case. Most of the energy coming out in the super Eddington case is coming out in the wind. The total amount of energy released in the kinetic outflows is larger than in the radiation field. So again, these are probably the most important result from the study so far has been measuring these efficiencies and to see how they change. So each point on here is a calculation we've done with a different spin or a different initial magnetic field geometry, plotted as a function of the mass accretion rate in terms of the Eddington ratio. And you can see this steep drop-off in the efficiency in the super Eddington case. These super Eddington disks uniformly are very weakly radiative. Their radiation efficiencies are very, very small. And that has important implications for the observability of these things. Because we're doing GR, we can study the actual plunging region and the formation of relativistic jets by Blandford-Znayak. We've been doing a lot of work to compare against GR models, analytic models for what the plunging region should look like. The matter doesn't just disappear at the ISCO in the black hole accretion flow, the innermost stable circular orbit. Instead, it has to fall into the horizon. There's still matter there, and that matter can produce photons, and it can also reflect photons, and so it has an observational signature, which is why it's important to be studying. But I won't say more. It's sort of another whole project. But some of the takeaways, observational takeaways, are that I know I'm covering a lot of material, so to make it sort of a soundbite, the sound bites are that highly super Eddington flows are not going to be highly luminous. We don't see highly super Eddington luminous quasars or accreting compact objects, but we don't expect to based on these calculations because the radiative efficiencies are so low. And moreover, the variability also shows interesting trends with accretion rate. These highly super Eddington flows are less variable than the near Eddington or sub Eddington. Again, something you can compare against data. Why? Because the photosphere is so far out, and it's very long time scales at very far out. And so at very, very large radii, the fluctuations are much less than they are near the horizon. You can never see the horizon in these super Eddington flows. You're only seeing things at 100 or 200 Rg. And so the variability out there is just much, much less. And so you'd expect these super Eddington flows to be much, much variable. And so obviously, there's a lot of interest in so-called LRDs, little red dots lately, discovered by JWST. They might be super Eddington accretion sources, and so comparing these kind of calculations in the super Eddington case to these LRDs is something that we're beginning to look at a lot. So to sort of broaden things a little bit, it's all very interesting to focus on the dynamics of these black hole accretion flows. And right now we're looking at spectra and doing frequency-dependent transport models so we can look at AGN. In AGN, the opacities are much more complicated, and gray assumption is not very good, so you really have to move to frequency-dependent transport. But there's another interesting question, which is how does the plasma get down there in the first place? We start with these donuts of plasma, and we evolve them from that initial condition. But how does that donut get there in the first place? Of course, we just put it there, but in nature, how does this plasma get into the black hole? That's another whole interesting problem that requires a different set of challenges to address, like I want to say a few words about. How are black holes fed? And this feeding and feedback is, of course, a very important problem in astrophysics right now because we think black hole feedback, and we can see observationally that black hole feedback affects macroscopic scales. So for example, in the Perseus cluster, you can see from this multi-wavelength image, you can see from the X-rays cavities and holes. where the jet from the central black hole has blown away bubbles or blown bubbles in the surrounding intercluster medium. And similarly, you can see in the optical, you can see these dense filaments, very, very, very dense filaments of optically emitting plasma, which also contain dust, so that you're seeing absorption in these dense filaments. And you're also seeing, broad swaths of cosmic rays emitting radio. And so clearly the accretion at the center is affecting things on the large scale. Can we calculate that? Can we understand that from direct modeling? It's a challenging problem because the length scale problem. You have to go from tens of kiloparsec scales to capture the galaxy, all the way down to the event horizon, milliparsec scales. And that's 5 or 6 orders of magnitude in radius, which corresponds to more orders of magnitude in time scales. We want to start a calculation at the kiloparsec scale, on the galaxy scale, and we want to go all the way down to the horizon, where I've put in a little EHT image in there to, hopefully that triggers horizon in your mind. So how would you do that? Well, we use the standard sort of zoom technique that's been used in cosmology. You just use AMR to, you evolve the galaxy scale for, a few hundred million years, and then you refine the mesh to resolve inner scales, and you refine again, and you refine, and you just zoom in all the way down to the horizon and capture the dynamics of what's going on down at the smallest scales. And so this movie will sort of show you what's happening, starting from this hydrostatic equilibrium on the larger scales in a standard NFW potential, appropriate for a galaxy like M87. We add some velocity perturbations to this hydrostatic equilibrium just to get turbulence going. And as we zoom in from kiloparsec to tens of kiloparsecs to parsec scales, you see these cold filaments that we saw in the observations forming from thermal instability. So the calculation includes optically thin radiative cooling, and that cooling is being excited by the turbulence. It's generating these very, very thin, dense, cool filaments. This multi-phase medium has emerged self-consistently from the turbulence. Those filaments are now feeding the inner regions, falling in. They're not pressure supported anymore, so they're falling in. You zoom in again now to tens of parsec scales, and then you begin to see these filaments are actually feeding a little rotationally supported disk now at parsec scales in the center. This is actually getting strongly magnetized because along these filaments is dragging in magnetic field. You zoom in even further and you see there's a hole in the middle of this disk where actually quite hot, dense plasma is being produced. And that still is feeding material to smaller scales through little filaments. What did I just do? Still smaller filaments falling in. So now we're down to 1,000 RG scales, a tenth of a parsec. We're not quite there yet, one more to go. We finally zoom in all the way to tens of RG scales. We have a standard GRMHD simulation where it's a MAD. If those are familiar, you see these bubbles being formed by the MAD simulation. So we're all the way down to a MAD flow in the very, very, very center, being fed across these 5 orders of magnitude and scales. And allows you to begin to look at what the feedback is really doing here. So we're going from tens of kiloparsecs through these filaments to a disk, to a hole in the disk, to these dense filaments falling in to a GRMHD simulation at the very, very middle, where you're actually producing a jet. You've got a MAD flow, for the experts, this is magnetically arrested disk flows in the middle, strongly magnetized disk flow. Despite all that complexity, it turns out the structure is rather simple. Everything's a power law. Maybe people shouldn't be surprised. Everything's a power law. And it's an interesting power law. The mass accretion rate is going like r to the 1/2. Regardless of the magnetic field strength or geometry, hydro or not, I actually don't know of any prediction that says it should be r to the 1/2. There are many, many self-similar models for accretion flows in astrophysics, and I'm not aware of any of them that gives r to the 1/2, except perhaps the ADIOS model if you put the appropriate value for the wind loss rate is. So we're now repeating these calculations using a whole series of halos taken out of the illustrious TNG simulations. We take the potential and gas produced by illustrious TNG and we zoom in using this technique to look at how feedback works and across a much larger sample of halos. So that's kind of exciting to be able to connect directly these cosmological simulations with GRMHD simulations of feedback. But there's one more skeleton that I wanted to mention, which is that, well, the zooming in is all well and good, but the time step basically comes to a crashing halt as you zoom in. Because when you get down to the horizon scale, the time scale there is a few weeks. And so your time step is set to be a few weeks. There's no way you're going to evolve that for cosmological timescales. There's no way that this zoom method is ever going to allow you to study feedback to the larger scales on cosmological timescales. And so based on an idea from a student here in Cho at Harvard, and then a student at Princeton, Minghao Guo, has been working with us and Elliot Quadrat and Verkel Springer are involved in this as well, to try to accelerate this using something we call the cyclic zoom method, where we start from this mesh. Suppose you start from a mesh that's spanning this 5 orders of magnitude in scales I mentioned, from the Bondi radius all the way down to the horizon. Your time step there is minuscule, very, very slow. So what we do is we replace the inner part of the flow with a coarsened representation, basically de-refine it using AMR, and store and hold fixed this coarsened solution in the inner region as a mask. If there's a jet there, we have a jet coming out of the inner mask region. If there's infall, we keep this infall going in this mask region according to whatever this coarsened solution is. And we de-refine the mesh all the way out to a large radius, so the time step gets quite large, and then you can evolve the outer regions for many more dynamical times. And that results in a new representation of the outer flow. And then you zoom back in again so that the inner flow now responds to this new outer region. And of course, the time step comes to a crash, and you evolve it for a little while, but then you zoom back out again. And you do this hundreds of times, in and out, in and out, in and out, in and out. And this enables you to evolve this for cosmological timescales while still capturing the feedback produced on small scales, the production of jets and winds. If the jet changes power, direction, or whatever, it gets captured by these multiple instantations of the small scales during the evolution. When we first thought of doing this, I thought this will never work. And remarkably, it works beautifully. I mean, we tried as many test problems as we could think of, including things like hydro-Bondi flow, which has an analytic solution. And this cyclic zoom relaxes to the analytic solution within a fraction of a percent, 0.1%, almost immediately. So this shows you the radial profile of the accretion rate in a hydro test. For MHD, there's the Blandford-Zanaik solution. You can compare that you get that as a steady state. Cyclic zoom settles down to the Blandford-Zanaik solution with the right pointing flux and the right field geometry, again, after only a few cycles. So it reaches these steady state solutions immediately. And then even unsteady solutions, as soon as you add MHD to the Bondi solution, it's no longer a steady state solution anymore. It's no longer an analytic steady state. It's got this convective, buoyant flows. It's very, very time dependent. So what's the right answer in that case? Well, we don't really know. What we did is we just paid the price of doing a direct simulation with a fine mesh all the way to the horizon. We paid the price, ran that for months to get a reference solution, and then we ran cyclic zoom. In a few days, it reproduced the same solution, again, within 1%, not only for the profiles of things like the M dot, but also the efficiency, the energy ejected to large scales over many orders of magnitude. 4 orders of magnitude scale was all in agreement with the reference solution. And so that looked very promising. We've also run these accretion tori, where rather than just evolving the entire torus with the same mesh, we zoom in and out of the tori to run it for much longer. And it turns out there are sort of known solutions about how the mass accretion rate depends on spin, how the efficiency and the magnetic flux in the horizon phi, how those depend on the spin. And again, once again, cyclic zoom reproduces all those results directly against the direct solutions, the so-called reference solutions. These are big plots because these flows are highly variable. So there's no one defined value for the mass accretion rate. It fluctuates. So this is the 1 sigma fluctuations in the flow. And again, even those are in agreement with the direct solution. So we really think this has got a lot of promise for doing feedback. And in fact, we've already been using it to evolve accretion disks over ridiculous amounts of time. So here's the time evolution of a magnetized accretion disk in which MRI drives accretion over 10 million M, such that the disk is essentially completely accreted over that time scale. Most simulations run to around 20,000 to 60,000 M. So this is sort of 2 orders of magnitude longer than a typical GRMHD simulation might run for. And you can see how the mass accretion rate, for example, is changing with time. There's no such thing as a steady state accretion flow in this case, because it's just all dying away as either the disk expands or is lost in the wind, or it all gets accreted in the middle. And again, we can begin to look at how the radial profiles of the density, starting off with the torus, so it's all like it's all located in a particular radius in this torus, in this donut, and then it spreads out, and you can, there are analytic solutions, analytic predictions for how this spreading should occur, and so we're able to compare directly against those analytic solutions for how sort of the viscous spreading of a torus of plasma in GRMHD should work. Again, this is a regime that I don't think you could reach without cyclic zoom, and so it's been quite interesting for us, and I think it's going to enable more studies of black hole feedback and accretion on cosmological timescales. We're certainly pursuing it in many more problems. So I think I've given you a flavor of the kind of problems we can tackle at Exascale. My takeaways are that I love COCOS. It's great. It gives you this performance portability. Even I can get it. Even I can use it. Exascale enables you to include more physics, more algorithms. You can include radiation transport. You can include numerical relativity and include particles and do calculations that have all the multi-scale physics you need to compare against more realistic comparisons with data. And of course, you can study lots of new problems like radiation-dominated accretion flows, binary neutron star mergers, blah, 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 lots of things going on. And for those who are interested, students especially, there's a summer school that David Radice is organizing at Penn State University. If you want to know more about computational astrophysics and using AthenaK in particular, you might take note of this next summer. With that, I'll conclude.
Thank you. We have plenty of time for questions. Any questions from students? Yes.
What are you most excited about, in terms of open-ended questions that you think could be answered with exascale simulation technology?
Well, of course, they're all things that I'm currently working on, so it's probably no surprise. I think that we should be able to reproduce the spectra and time variability of accreting black holes directly, because we think the only important physics is MHD and radiation transport, and we have those. And GR, and we have those all built in. So if we are not able to reproduce the spectra of AGN, if we're not able to reproduce the spectra of X-ray binaries or some of their properties of variability, then we must be missing something fundamental. And I think that's very exciting to have a first principles prediction of what it no longer be prediction because we have so much data to compare against. We should be able to model that data directly. I think that's one very exciting for the future. The other thing I've been learning a lot about is relativity, which I think is a really open field. There's a lot of unsolved problems in relativity that I think computational methods are going to really help with. But it's such a complicated system of equations and expensive to evolve that I think everyone's been focused on binary black hole mergers for obvious reasons. But there are many, many other interesting problems to be looking at in numerical relativity, and I think that's another area that's very, very exciting. Not necessarily my expertise, but I think that's another area.
Hannelore.
I have like 1,000 questions, but can we go back to the slide where you were showing, in particular, the Maxwell and Reynolds stresses of one of these comparisons?
The red hydro stuff?
Repeat the question.
Yes. The question was to go back to the slide on the radial profiles.
There's an actual question, but it'll be easier to phrase
Yes.
to get there.
Here we go.
Okay, yeah, great, wonderful, thank you. So I'm looking at the super Eddington case, and so for MRI, obviously, you generally speaking expect the Maxwell stress to be out 3-4 times the Reynolds stress, right?
Mm-hmm.
And so I'm looking at the super Eddington, and you can see that's about right. But one thing that really struck me about the near Eddington is that you really do have a drastically lower Reynolds stress compared to the Maxwell stress than I would expect. And I was just wondering if you guys had looked very much at that, where again, like you're getting that typical, what looks to be your typical relation for the super Eddington case.
Yes.
And I'm a little surprised that it's that's recovering what you would expect for that
Right.
Maxwell-Reynolds stress, but you're not getting
Yeah.
it there.
A very perceptive question. I mean, that's focusing on an important detail. I would say that the near Eddington case, if you remember the image, it's highly structured. You have this thin gas pressure dominated layer, and then you have this magnetic corona above it. This stress is integrated over both the thickness of the disk and the corona. And the corona is contributing a lot of Maxwell stress and very little Reynolds stress. So I think that the reason why the near Eddington case Maxwell stress dominates so much is because of this structured flow, whereas the super Eddington, as you remember that, is a thick wedge. It's not stratified very much. You know, the fluid and the magnetic field are well mixed. And so I think that's the reason why.
I was wondering, can I get a second really quick thing that's just related to the same thing? Just have you painted those plasmoids and reconnection sheets onto your typical structured field reversals that you expect with MRI?
You mean from the very high resolution? So these calculations, of course, are not done at that high resolution, and so we don't have. So, but yeah, the goal of doing these very high resolution MRI calculations are to examine whether or not these plasmoids really make much difference. I mean, there's many goals, but one of the goals is to look at whether or not when you resolve the tearing mode produced by reconnection at very small scales in this turbulent flow, how much does that really change things? Does it really change the accretion rate alpha? Does it really change the dissipation rates or not? That's an open question in my view. There's been a lot of interest in the role of these plasmoid instabilities and that it might change the spectrum of turbulence. It's at high K, but they've been done in idealized problems. This is a nice problem because we have a fluid dynamical instability that drives turbulence, and we can then ask, what is the role of plasmoids in a really turbulent medium?
Putting a finer point on it, and then I promise I'll
Yeah,
shut
well,
up.
you can discuss it over dinner.
Hi.
Yeah.
Thanks for the nice talk. I'm interested in the cyclic zoom thing, and it's a simple question, but how do you pick the scale and periodicity of the zoom function?
Yep. So that's a free parameter. To start with, we just chose to evolve each level for roughly 3 or 4 dynamical times at that radius. So you evolve the outer scale for 3 or 4 dynamical times. You zoom in, you do that for 3 or 4 dynamical times. That's a shorter and shorter and shorter amount of time as you zoom all the way in. It's long enough for each level to come into equilibrium with whatever flow is there, but not so long that you're spending forever. Now, you can always change it. You can always zoom in and zoom out more frequently if you want, or less frequently. You can do these so-called W cycles, which are used in multigrid, if you're familiar with that. There's many, many, many options you can do to this, but the simplest thing right out of the box seemed to work pretty well. And so we haven't actually explored it that much.
So, Jim, I wanted to pick your brain a little bit more about these little red dots, which are curiosities with JW, and you're implying that they're super Eddington accretion.
Yes.
And do you think that explains the properties that we see? Lack of X-ray, lack of radio, and what is maybe you could tell us a little bit more about what your calculations
Right.
so far are revealing.
In my subjective opinion, I think that super Eddington accretion is an excellent explanation for little red dots. I would say that's very subjective. I would say that so far from these calculations, there are some properties of little red dots that are explained. For example, the lack of X-rays, because you'd only see them if you're looking straight down. The broad, the line widths in the winds, because you've got these strong winds. The lack of variability, because their photosphere is so far out. The most important property about LRDs is the spectrum and the Balmer break. For that, you really need to post-process this or do a better job. We haven't done that yet, and there's other people working on similar ideas. There's papers by Ramesh Narayan and others on. So I think it's possible, but it has not yet been shown definitively that little red dots are explained simply by these kind of accretion models. Now there's other models as well. I cannot, of course, Mitch is famously pursuing or kind of related really. It's a black hole at the center of a non-rotating cloud, but Basically, a black hole at the center, I think, is an excellent explanation, as opposed to a very dense stellar cluster, which seems to be alternative.
Erica.
Okay, so following up on that, some of them, and especially when there's not that many of them that actually have multi observations, but the ones that do, a lot of them do show variability. So is that going to be problematic for the super Eddington hypothesis?
I mean, I think we'd have to look at the level of variability. So far, all I've said is less variability than AGN, which are extremely variable. The thought would be that there should be less variability and on longer time scales than you would have seen for a typical, AGN. And I don't know whether that's true or not.
Yeah, we're
Still getting the data, or? Yeah. I'd be interested to know,
We have time for about 2 more questions. Go ahead.
Hi.
I'm a planetary and stellar person.
Okay.
And I was curious what, over your career, how the role of computational modeling has evolved over your career, and then how you see with exascale modeling and further as our computational power increases, how is that role going to continue to evolve?
Yeah, that's again an excellent question. I mean, obviously, it's evolved a lot. I would have said computation was a small component to most astrophysics when I got into it, and by necessity, it's gotten to be an enormous part of it now. I mean, there's hardly a paper written or a theory project that doesn't involve some level of computation. So I think it's completely embedded and clean, and I think it's great. I mean, at some level, computation is just another way to solve these equations. It's not magic. It's not, it's not making things up. It's just solving a bunch of PDEs on a computer instead of finding analytic solutions. And so, as long as it's done carefully and correctly, it's just another tool in the toolbox. I worry a little bit that computation is getting so complicated nowadays that in the future it's going to get less understood and maybe more abused, because, I mean, there's a lot of interest in doing AI, for example. And again, I don't know if this is being recorded. Maybe I shouldn't say.
Yeah.
But I mean, I don't. People say, well, why don't you just train a simulator and not spend all this computer time running Exascale? But it's all about the training sets, and we don't have a training set for super Eddington black hole accretion flow. So how are you going to? Certainly, you could train an emulator and then tell it to do that, but I just wouldn't believe anything it gave you. So similarly, I think you have to be careful. I think AI is an incredibly powerful tool. It's going to make lots of differences, but I just feel like as it gets more complicated and you have more ways of doing things, you have to be a little more careful about how you do them to make sure that at the end of the day, you're just getting the true solutions to the mathematical model you're trying to investigate, and you're really getting understanding out of it. So in some ways, it's getting harder, not easier.
So in terms of computational techniques and language models, I've gathered that you're a big advocate of the COCOS package.
Yes.
And would you recommend any other packages to also integrate into trying to learn how to do computations like this?
So the COCOS is really specifically focused on performance portability, being able to run your code on different architectures. It doesn't really, it's method agnostic. It's not about fluid dynamics or MHD or anything like that. So if you're only asking about how do I write portable code, there are other ways to do it. For example, there are open libraries like OpenCL, OpenACC, and they have their strengths and weaknesses too. Why didn't I use them? One weakness is that you rely on the vendor to provide a compiler that meets the standards, and there's not a lot of incentive for NVIDIA to write a compiler that actually implements all the features needed for OpenACC or whatever. And the beauty of COCOS is it fools the machine. I mean, the NVIDIA compiler has no idea that I didn't write my code in CUDA. So it takes advantages of all these machine-specific, hardware-specific performance enhancements that NVIDIA writes for CUDA and won't necessarily write for anything else. So basically, the vendors have no reason to write port. Why would they want you to run your code on anything else? So they have no reason to support and COCOS just takes that out of their hands. It does it behind the scenes, and so then